Hi everyone, we're going to listen now a video on conditional probabilities that follows the former videos on simple probabilities. So let's see the difference between both. Conditional probabilities are consider two events, given two events A and B that are not necessarily mutually exclusive. That means that they do have an intersection. Their own probability to occur without any other information are P of A and P of B. So each event has got its own probability. Now, an additional information has to be done or given. In general, if we do know that A occurred, then this information can make the probability of occurrence of B evaluate. P of B becomes P of B given A. So you have to write a subscript A. That means given A occurred. So it's proved that in this situation, the probability of B given A equals the probability of A into B divided by the probability of A. And we will better understand this formula with examples, of course. There is a special case in conditional probabilities. In case, and it's possible, the information A occurred doesn't affect P of B. So if P of B given A still equals P of B, then A and B are said independent. A consequence using the formula on the left is that P of A times P of B equals P of A into B. And this is the only situation where this formula is true. Okay, it's not a general formula, but it's met where A and B are independent events. So let's see all of these notions in 3 exercises. The first one explains that E is the set of integers between 1 to 10. A is the even numbers of E, or the set of even numbers of E, so 2, 4, 6, 8, and 10. And B is the set of multiples of 3 in E. The multiples of 3 are 3, 6, 6, and 9. Yes, 3, 6, and 9. I'm calling back all the formulas that we have and that we can use in such an exercise, okay? So general formulas here. The 3 rows are very important, of course. The formula in blue that is available only in equally likely outcomes inside omega. And the new formula for conditional probabilities. So let's display a Venn diagram of our example. So we can see the whole set E, the subset A of even numbers, and it's outside with odd numbers, and the subset B with multiples of 3, and the outside of B that contains all that is not a multiple of 3. Let's display now a new way to display results as a probability choice tree. So this is a choice tree that creates a separation between A and A bar in a first level. So you are dividing your global set into A and the outside of A. And then you are dividing A by the numbers that belong to B and those that doesn't or that don't belong to B. And same for the outside of A. You've got numbers that belong to B and numbers that don't belong to B. So you've got here your 4 subsets that has been created in the Venn diagram here, 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 and here. So the first question of the exercise asks us about a third way to represent the result, the contingency table, which is a very important tool that can be used in exercises on conditional probabilities. The contingency table crosses A bar and B bar without any order. So it's an advantage compared to a tree that uses a given order. We began by A and then we put B. But we could have done the contrary, the opposite situation. Okay, so a choice tree is a choice at the first. The contingency table shows the number of elements in the 4 different subsets that has been created. The 4 subsets in the tree are the 4 ends of the path of the tree. So you can see that in A you've got a total of 5 elements. Yes, they are here. And in details, 1 is in B and 4 are outside B. In A bar, you've got 5 elements again, but 2 are in B and 3 are outside B. And you can do a total for B and for B bar and confirm that there are 3 elements in B and 7 in B bar that the Venn diagram shows you. Okay, now questions about probabilities. Let's choose a number between 1 and 10 at random. What is the probability? It would be even. So let's choose a number at random inside the whole set. The probability it would be even is P of A. So you are in equally likely outcomes. Okay, every one of the 10 numbers has the same chances to be chosen, 1 chance in 10. In case of equally likely outcomes, the blue formula is available, and you just have to divide the cardinal number of A by the one of omega. So 5 over 10. What is the probability? It will be a multiple of 3. So with the same reasoning, 3 over 10. Now let's go in conditional probabilities. You've got here simple probabilities that are not conditional. Now, you want to choose a number between 1 and 10, and you just did it. You don't look at it, but someone tells you it's a multiple of 3. Now, what is the probability? It would be even. Well, if you know your number is a multiple of 3, you know that you are in the row B of your table. And in the row B, what is the probability of A? It's 1 chance in 3. So this is the probability of A given B. So exactly the opposite writing compared to the formula here, okay? It's P of A given B in this question. So now, what would give the corresponding formula? The formula would give you P of A given B equals P of A into B divided by P of B. But you know P of A into B. P of A into B is 1 in 10. And P of B is 3 in 10. So 1 in 3 in the end, okay? You just fall on the same result than earlier. I just displayed probabilities on the tree in order to talk about them, okay? And to say a little bit more than asked in the exercise. So in a tree, you have to put probabilities on a line to express the probability to go from the beginning of the line to the end of the line, okay? So there is the set E at the beginning, E. And the probability to fall into A is 1 in 2. Then, if you are in A, the probability to fall into B is 1 in 5. Okay, if you are into A, the probability to fall into B is 1 in 5. And if you are outside A, the probability to fall into B is 2 in 5. Okay, so this is not the same, of course. The proportion of elements of B inside A is not the same as the proportion of elements of B outside A. So you've got, by definition, conditional probabilities in the second level of the tree. Okay, simple probabilities in the first level, conditional probabilities in the second level. And the conditional probability that has been asked in the question 3 is not given in the tree. So that's a shame, okay? Using a tree to find whatever conditional probability you want is sometimes easy, so you can read it here, or sometimes difficult because you have to perform a calculation. So we'll see it in additional exercise more clearly. But the table is clear, okay? The probability of A given B, so inside B, is 1 in 3. So by the way, the probability of A, the simple probability, was 1 in 2, 1 change in 2. And if we know that B occurred, the probability of A has changed. So we can say that A and B are not independent. Now, next question. We are taking a number between 1 and 10 at random, and we're told it's even. Oh, you've got an even number. So in the table, you are in A. What is the probability? It would be a multiple of 3 then. So what is the probability of B inside A? It's 1 in 5. Okay, and this time the tree confirms this result. The probability of B given A is 1 in 5. But your tree has been built thanks to the table. So the first and most important tool is the table. The corresponding formula in green here would be given P of A into B divided by P of A, so 1 in 10 divided by 1 in 2, or 5 in 10. So in the end, 1 in 5. So we can understand this general formula by the way that it makes us divide two probabilities that lead to the result that we expected thanks to the table. This formula is not necessary, okay? If you've got the table, you don't need any formula, and that's a change for the conditional probabilities calculation. Next exercise. Let's take a completely different example. A laboratory has developed a breathalyzer, in French, an éthylotest. A reliability test has been done on this product with a test population on which it's been stated that 2% exceed 0.5 grams per liter. It's the event E, exceeds. Okay, so physicists have tested people, okay, with their blood and know that exactly 2% of them has a rate of alcohol in their blood that is more than 0.5. Okay, so are out of law. Everyone exhales into the breathalyzer. The event P refers to a positive result given by this device. And no device in the world is perfect. Thus, the following. the reliability test has given the following result: 95% of people who really exceeds 0.5 got a positive result. So the device makes a mistake for 5% of such people. And at the opposite, 96% of people who don't exceed 0.5 got a negative result by the breathalyzer. So the device makes a mistake for 4% of people. Okay, so its reliability percentage is not bad, okay? 95% for a part of a population and 96% for the other part. Now, the question is, what is then your probability of really exceeding 0.5, given that your result is positive? So you exhale into the breathalyzer. The breathalyzer says or displays positive. You are positive. What are your chances? What is your probability of really exceeding 0.5 in your blood? So let's build a tree. Why not? Let's make a separation between A and E bar for the population. 2% exceeds. Okay, so 2% are into A and 98% are not. Among people that are here, 95% will be tested positive by the device. And so 5% correspond to a mistake of the device. In the other part of the population, 4% correspond to a mistake. The breathalyzer says positive, whereas you were not exceeding 0.5. And 96% has a result that is a negative one. Okay, the tree expresses the data of the exercise. Now let's perform calculations. What is the question? The probability of E given P. P of E given P. So by the use of this formula, E is B and P is A. Okay, let's write it. Now we need to develop the calculation because we didn't build a table, okay? So how could we reach the probabilities of intersections thanks to the tree? Well, this formula is able to tell you that P of P into E equals P of P times P of E given P. But this is true also that P of P into E equals P of E times P of P given E. Okay, there is a double way to calculate the probability of intersection. And the second one can be seen in the tree. P of E multiplied by P of P given E will give you P of P into E. A probability of intersection coming from a tree is accessible by the multiplication of probabilities that you encounter in a path of the tree. On the other side, okay, on the low part of the fraction, P of P. P of P is not given in the tree and is not given either in the exercise, of course. The tree and the exercise are the same, contain the same information. The probability of P can be reached thanks to the last but one formula here. P of P can be seen as P of P into E plus P of P into E bar. So let's write it. So you need 3 intersection probabilities in order to perform your calculation. And intersection probabilities come from the end of the tree. Okay, so let's write now the calculations. The first one is 0.02 times 0.95. the result 0.019, okay, or 1.9%. Below, you've got the same. So you just have to write it again, but you have to add the second one, that is P of P inter E bar, that is reached here. Okay, 0.98 times 0.04. The result is 32.65%. Okay, a little bit less than 1 in 3. So, if this device says that you are positive, the chance that you really exceed 0.5 grams per liter are 32%. So it's an astonishing result, but it's true, of course. We didn't make a mistake in our calculations. How could it be possible? It's not very easy to see it if we use the formulas and the tree. But it will be very simple if we have a look at a contingency table. That's why I'm telling you again that the contingency table is the most important tool that you have to use in conditional probabilities. So let's see it. You've got a false positive paradox, and it's a well-known paradox in statistics and in probabilities. A false positive. You are tested positive, but it's false most of the time. So let's build a table with 10,000 people as an example of the total number of people, whatever the total. So you just have to take a round number that is a simple one. And let's read again the exercise. 2% of them are in E. So that represents 200 people. And 9,800 people are not in E. Okay. So now what for P and P bar? If you are in E, 95% of the time you are tested positive. So 95% of the 200 people are here in the first cell. And that represents 190 people. And below, 10 people has been tested negative, even though they were exceeding 0.5. Okay, so the first mistake of the test. The test tells you you are negative, whereas you were meant to be positive. It's a mistake. Secondly, on the right, for people who are not exceeding 0.5, there is a mistake of the device. Only, I could say only, 9,408 people will be tested negative, but 392 people will be tested positive. It's exactly 4% of these people. And this number is 96% of these people. So now, if you have an horizontal look at your table, you can see that in the subset of positive tested people, the people that are exceeding 0.5 are in a minority, and the majority are here. Okay, the mistake of the device created this false positive paradox. Okay, because the positive tests correspond in majority to people that wouldn't have been to be tested positive. And you can see that the probability of E given P is the proportion of E inside P. And this is 190 divided by 582. But 190 divided by 582 are exactly the calculation that we performed earlier. This is the same proportion, and this proportion is 32.65%. Okay, so the table is the thing to do in such an exercise. Okay, last exercise, 23 of our document. Taking back exercise 22, so just the exercise we just finished. Are A and B independent? Well, let's call back the definition of independence. Two events A and B are independent if P of A into B equals P of A times P of B. That's one way to see it. Or the former definition, if P of B doesn't depend on the fact that A occurred or not, or we don't know. Okay, P of B doesn't change. So let's see it now by calling back the tree. And you can see easily that P of P given E is not the same at all than P of B as P of B given E bar. 95%, 4%. So if you have a look at that, you can say, no, they are not independent. They are very dependent events. So let's check the dependence thanks to this formula, the first one. P of P into E equals 0.01 or 0.09, sorry. And P of P times P of E was this number times this one. You can perform this calculation and you can see that this is absolutely not the same result. This one is approximately 10 times more little than this one. Okay, there is a big difference between both. The definition now is P of P given E equal to P of P given E bar. So no, in the tree you can see that it's completely wrong. So P and P are dependent and very dependent. Now with exercise 18, are A and B independent? So let's go back to the statement of this exercise. A random experiment consists in taking one integer at random among 1 to 20. So it's a former exercise in a former video. The event A is get at least 15, and the event B get an even number. Okay, so let's go back now the graph, the Venn diagram of every possibilities. Okay, so you've got the set of at least 15. That is 15, 17, 19, 16, 18, 20. And so that's A. And B represent the set of the even numbers. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And of course, the three last belong to A and B at the same time. So they are A into B. The outside of A union B represents numbers that are not written here. The numbers that remain are 1, 3, 5, 7, 9, 11, and 13. Okay, that's A bar into B bar or A union B with a big bar. So that's the photograph of our exercise. Now, are A and B independent? If you take this definition, you can ask to yourself whether P of B equals P of B given A. And this is a good point that the probability begins with the letter P, because you can see that at a proportion is the proportion of B inside omega equal to the proportion of B inside A? This is the same question. So let's check first with this kind of formula in order to have a result. P of A into B is 3 divided by 20. The result is 0.15 or 5%. P of A times P of B equals 6 on 20 times 10 on 20. And you can check that this is the same result. So yes, they are independent thanks to this result. Now let's go back to our thinking. Is the proportion of elements of B inside omega the same as the proportion of elements of B inside A? The proportion of elements of B inside omega is 10 divided by 20, so 50%. The proportion of elements of B inside A is 3 divided by 6, 50%. So this is a special case. In this scheme, yes, the two proportions are equal. And that means, again, that the proportion of B outside A will be the same. If you've got one equality here, you will obtain the second one, even if you don't calculate it. Okay, it will be the same. And you can see that the proportion of B outside A is 1, 2, 3, 4, 5, 6, 7 divided by 14. That are the number of elements outside A. 7 divided by 14 is 50%. Okay, so now you know everything that has to be known in this topic of conditional probabilities. Thank you, bye, and see you in the next video.